As we look to begin this problem, as I would always suggest, read through the problem first, then try to work it out on your own, and then watch the video showing how I approach it and how I went about doing it. And that'll be the best help and the best way to learn from this problem. So take this moment, pause the video, and do that. As I so often like to do, I've drawn a picture to represent this situation because I want to be able to see what is really happening here and what kind of shapes end up coming out of this story problem here. You'll notice that I've got a triangle being formed, and we can actually get a little bit more detail in here. Now, first of all, notice what this picture really represents. I've got my blue line here representing my ladder that's leaning up against the building. Then I've got my building over here on the left-hand side, and then the ground, of course, along the bottom. And I am hoping, of course, that they built this building so that it is intersecting the ground at a right angle. So notice a right triangle is popping out of this problem. So already I should be thinking about, okay, right triangles and what equations I know about those. But of course, we need to know, okay, do I want like Pythagorean theorem? Do I want area of a triangle? What type of formula am I going to use? So let's start putting in the numbers and figuring out what it is that we're looking for. So I'm going to label all the numbers that I see in the original problem. So I know the ladder is 17 feet long. I know it is sliding down at a rate of 4 feet per second. So that's sliding down, remember it's decreasing, that's going to be important, by 4 feet per second. And the last number that we know is that the base is 8 feet from the house. So I'm going to go ahead and label that as 8 feet right there. And then I'm trying to figure out, finally, the last thing is how fast is the bottom of the ladder sliding out from the base of the house. So it's trying to then figure out how quickly is this number changing. So I need to label that length as a variable name. So that's going to be W in this case, because it's the width of my triangle. So that means I'm trying to figure out how fast W is changing. In other words, my destination is dW over dt. All right, so that tells me that since I'm dealing with a length, I can be using Pythagorean theorem here. So I'm going to start putting in Pythagorean theorem here. So that's a squared plus b squared equals c squared. In this case, that's going to be w squared plus, well, this length squared. I haven't given that a name yet, so I need to give that a name. I'm going to go ahead and call that h, because I'm going with height of the triangle. Or if you really wanted to be creative here, you could think of it as the distance along the house. That would also make sense for h. And then for this last part, this is going to be the length of my ladder. Now, because the length of the ladder is not changing, technically speaking, you could actually just go ahead and call it 17 here. But I do like to not have to worry about that stuff as I go, so I am going to give it a variable name. I'm going to call it L for the length of the ladder. So I'm going to say it equals L squared. And now that I'm here, I can go ahead and figure out what the derivative is with respect to time. And now that I've found my derivative with respect to time, I can now start plugging in values. Now, do this on your own first if you haven't already, and then check it against my work here. And then I have now put up the work, but there's an error in here, specifically and purposefully. I'd like you to see if you can find the error in that work. And then I would suggest you pause it to look over this. And then once you've decided where it is, then go ahead and press play again. Now your eye might have been drawn initially to the 15 here because you might be thinking, where's this 15 coming from? There's no 15 in the original problem, so that must be an issue. But actually that part is solid. That 15 comes from doing Pythagorean theorem to solve for h. Because if we do Pythagorean theorem with the lengths that we do know, we could solve it and figure out that h should equal 15. Okay, so if that's not the error, did you notice the 4 that was with it? Because that would be this 4, right? But remember I made a point of mentioning that it was decreasing. The fact that it's decreasing makes a big difference. That means we must have a negative written out front of that 4 to show that it is a decreasing value. So if you didn't catch that yourself, be very aware of that. Whenever a length is shrinking, you have to say that the rate is negative there. All right, from here, now that we've gotten this much, now it's just a matter of doing the algebra to solve it for dW over dt. And when all is said and done, we find out that we got dw over dt value, in other words, how fast the width is changing, is 7.5 feet per second. Which means, if you think about it here, that even though the base of the ladder is 8 feet away from the wall right now, in just 1 second, it'll be almost twice as far away. The base of that ladder is moving out really quick here compared to where it currently is. All right, then this problem is done. Now, I'm kind of hearing in my head maybe somebody screaming about why was this a 0? And I didn't explain that at the time. So let's take a moment here and just make sure that we see that the reason why that was a 0 is because that is the dl over dt. That's how fast the value of L is changing. L is my ladder. My ladder is 17 feet long, always. That's a fixed value. Our ladder is not shrinking. Our ladder is not expanding as it slides down. And so that's why the rate at which the ladder is changing is 0. It's also why I said that if I wanted to actually use the 17 there, I could have. We have to use variables for anything that is changing over time, like our h value was changing. But if something isn't changing, yeah, you could go ahead and just put the number in.